Hi, my name is Toni from the Software Architecture Group at HPI Potsdam, and I welcome you to an introduction to a new dataset for evaluating regression test prioritization called RTPTorrent. Let's talk about tests. So, with tests we usually refer to a piece of code which validates some expectation you have on the production code. For example, in the form of a JUnit test case. And in larger projects, you might have a lot of tests exercising your production code. One problem here is that running these tests takes a lot of time. So we might detect faults which we introduce into our production code later in the build cycle when they're harder to fix. And the goal of regression test prioritization is to run these tests first, which are most relevant to our current task, so that we can detect faults earlier, get immediate feedback on what went wrong, and we can repair them when it's easier. Now, our question is, how do we know our RTP strategy is good? We have some standardized metrics for that. For example, we can compare individual test runs using a metric where we just plot a curve above the tests, going up whenever we see a test failure, and the area under this curve is what is called average percentage of faults detected, short APFD. There are also variations of that accounting for the length of tests or the cost of individual faults. So we can measure that, we can average it over several test schedules and get a metric how well our RTP strategy performs. The problem with that is, in practice, we don't really know which types of faults are used, which programs contain these faults, and which tests have been run to obtain these test schedules. And to build our understanding of how this happens in practice, we did a literature study. In our literature study, we reviewed 8 venues and 1 survey paper, which is the latest one in 2019 we could find. And we extracted 10,000 publications, of which 1,400 had actually mentioned the term test and prioritization in one or the other way of spelling in their keywords or title. And of them, 117 actually used a dataset of programs to evaluate their regression test prioritization strategy. So these are the core papers of our literature study, and we analyzed them with regard to which programs they have used, how the variants of that program came to be, like were these like git commits or versions, which tests have been run, and which faults were introduced to make tests fail. We especially distinguished between historical variance tests and failures, which occurred during the development of the program, so they represent real programming activity. We distinguished them from the manual and generated variance tests and faults, which were only introduced for study purposes, either in a manual way or, for example, through mutation testing, which would be a generated way to get new faults. So here is an example of the type of paragraph we were looking when we were searching through the papers. Here the authors state that they used the Siemens suite for their evaluation dataset, and actually many papers use this dataset. So this is a dataset from the software infrastructure repository, and the programs here are very small, so they are less than 1,000 lines of code, and every study on average only has a little bit more than 5 projects. So although these are real projects, which is cool, we see that these do not really reflect the way we as programmers would interact with software today. So the practical projects where RTP becomes important are much larger than 1,000 lines of code. What we also observe is a lot of manually seeded faults. These do not represent like real programming activity. Another thing we analyzed was the sharing and reuse of the individual study subjects. Actually, 58% of our papers reused one or the other dataset, but mostly this is focused around the software infrastructure repository. So again, they kind of repeat their studies on very small projects. And what we also observed is that at many places they describe the program and the tests they run, but we would have no access to the actual test runs. So we can only see the aggregate statistics in the end. For example, the APFD score is a box plot, but we wouldn't be able to see which tests have been run, which tests have been failed, and that makes it a little difficult to compare different test schedules across literature. So we have a limit of reproducibility here. So we identified a couple of challenges from that. So first, if we have these few or small projects in the study, what we'd like to complement that with is projects which are representative of their respective ecosystem. And also we see a lot of clean room studies with manual and generated faults, which is cool because you can explore all the edge cases, so you get like very high internal validity. You can do very clean measurements of your individual metrics. However, this does not reflect the realistic noisy behavior of programmers. A simple question we can ask but not compare to any of these studies, for example, is what if they had just run the most recently failing test first? So that's nothing we can answer with the data we have so far in the studies. Also, reproducibility is a bit limited. So what we'd like to have is very fine-grained test results, so that we are not reliant on comparing the average APFDs in the end with the other paper, but we can compare their schedules to our schedules. So that's a challenge we want to tackle now with our new dataset. Now let's have a look at the dataset itself. So RTPTorrent consists of 20 open source Java projects from GitHub, ranging from 10 to 670,000 lines of code, and over 20 million test case runs in the time frame between 2007 and 2016. The dataset itself was constructed based on 2 other datasets. That's also where the name comes from. So we are based on GHTorrent, which at the time of writing contained 125 million GitHub projects and 1.4 billion commits and all the metadata. And we also used TravisTorrent, which contains 3.7 million build results and log files, which we used as an entry point. So let's look at TravisTorrent in detail. So while the TravisTorrent table has a lot of columns, what we're interested in is these 3 columns. We have a unique identifier for the Travis build job. We have a project name, and we know whether this build is successful or not. So based on that, we can decide which projects look interesting by selecting projects that have a lot of builds. Some of them are successful, some of them are failing, so that we get real failure data here. And we know these projects are Java projects because we can look up their project language in the GHTorrent dataset. Also, we selected 110,000 jobs, which are basically all jobs of these 20 Java projects. Now we look at the log files. The log files typically have the job ID at the end of the file name, so we can identify them. And in this log files there is a lot of noisy debug output, but at some point we see test results. So we parse the log files looking for these exact test results for the state, the test case, which you can extract using regular expressions, and we can extract the test runs and failures and errors and skip tests and how long the tests took, also using regular expressions again. We don't do this for the whole build file. We only identify these interesting regions, like separated by the minus delimiters here. And that's how we get our basic data. So we fill our CSV files with the result of this parsing and a bit of sanitation. In the end, we ended up with 23 million test case runs and over 150 million test methods around, like if we sum over this count column in its individual CSV files. So that's the core of the RTPTorrent dataset. We also try to link this dataset to other sources, for example, from the GHTorrent MongoDB dump, which stores the raw API answers from GitHub. We can look up which files have been edited for each individual commit included in certain build jobs. So that allows new RTP strategies which rely on the file changes, for example. Now, an important question is whether this dataset is representative of the data we found on GitHub. So we analyzed all Java projects on GitHub, which are 6.4 million. And we looked if the contribution or the commit count in our projects is representative of the overall contributions across the Java community. The first thing we noticed is that the data we see on GitHub has an extreme power law distribution. That means a large percentage of commits actually are concentrated on a very small set of projects. So it doesn't come as a surprise that 97% of the Java projects on GitHub are smaller than our smallest project with the least contributors here. But only very few projects are larger than our largest project. So when it comes to representativeness or ecological validity, you can say this that the RTPTorrent dataset is representative of the larger Java projects, which is not that big of a problem, because these larger Java projects already cover 77% of all activity that happens in Java on GitHub, and regression test prioritization also becomes more important for these larger projects. We did a similar study with the author counts, see that most projects have less authors than our smallest project, which has 7 authors, but only a very small percentage has more authors than the 645 of our largest project. Coming back to the challenges we'd like to address, we wanted projects which are representative of the ecosystem and represent realistic behavior of programmers. It's probably not representative of certain industry categories, but concerning GitHub, at least we're representative of these larger projects. Concerning reproducibility, we have, if you think of this CSV file, very fine-grained test results here. So we can basically apply any metric to evaluate our test schedules. There's some remaining limitations. For example, there's only 20 projects, and based on the way we constructed it, it would be possible to add more projects. So this is clearly future work we can do, but what we can't do is get the projects to compile and run nowadays, because most of them don't really run out of the box, especially if you choose an older version. So the dependencies that are missing is very difficult to get it set up. So everything relying on dynamic execution or instrumentation of the projects will probably be difficult to reproduce using our dataset. Also, the data ends in 2016, which is a limitation of the underlying Regression dataset, which we used as entry point. So there's not much we can do about that. Okay, so how do we prioritize recent failures using this dataset? Well, we can now answer this question. So we conduct a very small study, we used our data, and we prioritize the most recently failing tests, so that the test failure gets executed first in the next schedule. And we recompute priorities using an exponential average here, or exponential smoothing. This whole technique is called demonstrated fault effectiveness. It basically prioritizes tests based on how much they failed in the recent runs. So in this example, when you have the prioritized run and the result from the prioritized run, we can kind of rearrange the test for the next run, running the failing test first again, and computing the new priorities. We can measure the APFD of that over the whole dataset, which is 81%, which is cool because it's about state of the art of 2015. So in 2015, which was the year RTPTorrent was released, one of the papers of XC 2015, which outperformed many of the existing strategies, reached APFD score of 79%. So we included this as sort of non-trivial baseline in our dataset, so you can compare against this strategy. So to sum this up, in literature we found very limited ecological validity and very limited reproducibility, and we wanted to fix that in our own studies. So we collected RTPTorrent, which is a dataset of 20 Java-based projects from GitHub and Travis CI. And this contains 23 million test case runs, which are very fine-grained. And finally, we can say that if you're looking for a very simple regression test prioritization strategy, then running the most recently failed test is probably a good idea. So here's the dataset link, and I'm happy to answer any questions.